Thanks, Daryl. Thanks for inviting me to talk about my favorite topic nowadays, which is running applications on near-term quantum computers. The overview of my talk is, I know a lot of people, like you mentioned, that a lot of people here are, just getting started with quantum computing. So I'll start off with a very gentle introduction to quantum computing. And then move on to talking about near-term intermediate scale quantum computers. And then next I'll be talking about running some applications on real NISQ computers. Okay, so I'll start with the introduction. So qubits are the fundamental unit of quantum information. So generally any talk on quantum computing will start with qubits. So what are they? So just like classical computers run on bits, which can be in a state of 0 or 1, quantum bits or qubits, you can represent them by vectors in a 2D vector space. So sorry, can people see my mouse?
Yes.
Yes. Okay, cool. Yeah. So qubits, analogous to a classical bit, a qubit is a vector in a 2D vector space. And an example of a qubit would be a state, an example of a qubit state would be something like this. In this 2D vector space, you can define a computational basis. And for instance, an example of a computational basis would be two linearly independent vectors that could be defined as 1, 0 and 0, 1. In this, sorry, who's scribbling? Is somebody making these marks? Anyway.
Yeah, Terrell, maybe let's fix this before we move forward. Terrell, do you have annotation turned on as an option for people? Terrell, are you there?
Oh, sorry, I'm mute. Yeah, I'm looking. I don't have it listed. Hold on.
And as host, maybe are you able to clear the current annotation?
Yeah, I don't have it.
Maybe just one check. Sonika, are you able to clear the annotation?
Yeah, you got yeah, up at the top menu there, if I remember correctly, in options.
Yeah, I'm clear all drawings. Yes, there we go.
You got it? And can you turn it off?
It
should be on the same menu.
Does anyone see an option?
Only you would see it.
Oh, okay. Nobody else is being able to see that. I don't actually.
Okay, let's just see what happens here.
Yes, let's hope it doesn't happen again. Okay. Okay. So yeah, so as I was saying, in this 2D vector space, you can define two linearly independent vectors, and that's your computational basis. And then you can write any qubit state in terms of these two vectors. And then this qubit state is called a superposition of the computational basis states, in this case, the 0 and 1 states. Right, so an example of that is given over here. And note that, what are called the amplitudes of these basis states can be complex numbers. They don't necessarily have to be real. So that's very different from classical computing. When you measure a qubit, so even though a qubit can exist in this superposition, when you measure it, it collapses into a computational basis state. And so, for example, if you had a superposition with these complex numbers alpha and beta, alpha 0 plus beta 1, the probability of measuring a 0 would be alpha square, and the probability of measuring a 1 would be a beta square, right? And then, of course, the sum of probabilities is equal to 1, and that sets the normalization of the vector in this 2D vector space, right? So this is the fundamental unit of quantum information. This vector. Okay. Then what happened? So this was what this was the state of one qubit. What happens when you have many qubits? So as the number of qubits increases, the size of the computational basis will increase exponentially. So for example, for 2 qubits, you would have 4 basis states. And for 3 qubits, you would have 8 and so on. And to be able to access states in this entangled basis, in this basis requires entanglement. So an example of an entangling operation, for instance, is a C0 operation. So if one of your qubits is in state X, the other one is in state Y, the C0 gate will send it to X and X C0 Y. And then and so if you have a general state in this basis of 2 qubits, represented by these complex numbers alpha, beta, gamma, delta, when you act a C0 operation on them, it will go to another state in this 2 qubit basis, right? And what excites people about quantum computing is that due to this exponential growth, for instance, if you had 50 entangled qubits, you would have more states than any possible supercomputer could store. And if you had 300 entangled qubits, you would have more states than the atoms in the universe, right? However, the caveat is that, one of the caveats is that quantum information is extremely fragile. So even though you have this very large state space, the information that you store in it will be easily destroyed by things like a small coupling to the environment. If it's stuck by a photon or a phonon or anything like that, you can destroy your information, right? And so this what I was talking about was the quantum state space, but obviously we live in the classical world. So in order to access that quantum information, we have to think about the quantum classical interface. What you realize is that the catch in accessing that information is that it comes when you try to put information into the quantum computer and try to take it out of the quantum computer. So putting information into the quantum computer requires you to do state preparation, which is prepare a quantum state. And typically this is done in the your starting state of your quantum computer will be a computational basis state or some very low entangled state that is easy to prepare. So the amount of information you can put into the quantum computer in the beginning is limited. And in the end, when you do measurement, you collapse to a computational basis state. And therefore, also you get out a limited amount of information out of the quantum computer, right? And just as an aside, like when you measure qubits, you can also measure a few qubits. You don't have to measure all of them. And that's a detail that might be important later in the talk. And so, with this basic description, right, the basic unit of quantum information, what happens when you entangle them, and, the restrictions on getting information in and out of the quantum computer, what are some kinds of quantum algorithms? So for instance, if you think about Grover's search, that's basically a quantum algorithm that finds a trajectory through this quantum state space that results in a desired state with high probability. So that's one kind of way of thinking about quantum algorithms, that you're traveling through Hilbert space, trying to get to a desired computational basis state in that space. Then another would be, so earlier we talked about the probability distribution of that results when you try to measure a quantum state. And so one class of quantum algorithms is around, generating desired probability distributions for sampling. And one example of this, one application of this is in generative machine learning, where you're trying to generate probability distributions that resemble the probability distribution of some data set. Then another kind of example is simulations, right? So for example, if you want to study interacting electrons, you can do certain transformations that map electrons to qubits. And then, if you wanted to study the system of interacting electrons, for one of the things you might want to do is time evolve it under a certain Hamiltonian. And so instead you can implement that Hamiltonian on your quantum computer and study that system by proxy almost. Right? So these are the kinds of quantum algorithms. These are some examples of quantum algorithms that are compliant with, with the restrictions we have on quantum computers. Right? Any questions up till here?
I think most of us would be with you.
Okay, cool,
Yep.
great.
Yep.
Okay. And then one interesting thing about quantum computers is that they can be realized on many platforms. So I know that mostly like classical computers are realized on silicon chips. In contrast to that, quantum computers right now are realized on a diversity of physical platforms. So, my company works on trapped ions. There are many companies like Google and IBM and others that will work on, and Rigetti, for instance, that work on superconducting qubits. There are some technologies that are at an experimental stage, such as nitrogen vacancies in diamond or quantum dots. There's some technologies that are, such as Majorana fermions, that are being pursued. That's being pursued by Microsoft, for instance. That holds a lot of promise, but they haven't been able to demonstrate a qubit yet. And then there are some, there's some proposals for quantum computation that are completely theoretical, that as far as I know have not been implemented exactly, but in theory you could, build a quantum computer on, for example, fermions, right, instead of qubits. So, just the message of this slide is that there's a lot of technologies that are in the running right now for building quantum computers. Then let's move on to some, I've described to you what qubits are and how they're physically implemented. Let's talk about what are some common qubit level operations. So what are the quantum logic gates? So in contrast to classical logic gates, quantum logic gates are always unitary. So they are reversible, and they preserve what would be called the length of the vector. In the beginning I introduced the vector, the length of that vector. And so examples of common quantum logic gates would be like a Hadamard gate, which sends a 0 to 0 plus 1 and a 1 to 0 minus 1. Then these Pauli matrices X, Y, and Z that so these qubits, these operations act on single qubits, and then some 2-qubit operations would be, for example, a swap gate, which swaps the state of 2 qubits. And then you can also have control versions of gates. So, for instance, in this one, if the top qubit is in 0, nothing happens. And if the top qubit is in 1, the operation U is the operation U acts on the bottom qubit. I assume everyone's familiar with this notation. There'll be a lot of this coming up.
Okay. Sonika, can I ask you a question about the last slide quickly?
Sure.
I don't know if you could speak to it or not, but fermionic quantum computation that's not really a phrase I've heard. That suggests to me that it's a different way of computing. Different than perhaps maybe the gate model, like adiabatic is different. Is it that different, or is it a gate model?
I think it would. It's still gate model in the sense that you can define quantum logic gates, but those gates probably look very different than they do on qubits. So what I was saying to you in the beginning, right, that you don't necessarily need to define even if you restrict yourself to gate model quantum computing, it's not necessary to define it in terms of qubits, right? Define it in terms of any quantum system. So it could be fermions, it could be, qubits, qubits, whatever you want.
You're referring to that conversation we had before we officially got started.
Yes, exactly.
Okay, all right. Thank you.
Right. And so the current programming paradigm for across all the different technologies that are on the cloud right now is quantum circuits. It's a pretty low-level programming paradigm, but it's the best we have right now. And this is a model in which quantum computation is a sequence of quantum gates, so of the kind that I was describing on the last slide. So, for example, if you look at a common quantum, quantum routine like the quantum Fourier transform, this is what a quantum circuit is going to look like. So the way to read this diagram, it's almost like a musical score, right? So on the horizontal axis is time, right? And each vertical time slot corresponds to the action of a quantum gate, right? So for instance, this box is signifying a Hadamard gate acting on the top qubit, and then this box, this symbol is signifying a controlled rotation gate acting between the top and the next to top qubit, and so on, right? If you run this whole circuit, what would happen is that if your starting state of your system was in a computational basis state X, it would be taken into a state that looked like this, right? And then, of course, what happens is that initially you don't need to be in one computational basis state X. You can be in a superposition of many of these computational basis states. And that's where the power of quantum computing comes from.
I just do a check here. Mm-hmm. So I'm looking at the rotation
mm-hmm.
gate or matrix, and in this diagram, you've got a controlled Z rotation.
RZ, yes.
RZ, and so, but beneath that, you're showing the matrix or the operator, I guess you'd call it. I'm trying to get my vocabulary right here. But if that was a controlled Z rotation, then those four, that 2 by 2 would be the bottom right 2 by 2 of a 4 by 4 because it's a control.
Yes, exactly.
Right? Okay.
Right. So if we go back to here, right? So if we
exactly, yep.
That you would just replace that over here.
Okay.
Right.
Thank you. Just confirming.
Yeah. Thanks for that. Yeah. So this is basically how we program quantum computers nowadays. We we sort of put together these 1 and 2 qubit gates, and we have some routines that maybe some some software packages might have this quantum Fourier transform stored in a library, and then you can just call it. But still, the programming paradigm is just still these quantum circuits, which I personally think is too low level. Anyway, so we were just talking about gate model quantum computers. So what are they? I'm calling them universal quantum computers here. But basically, universal quantum computers, they can perform any computation, and they can be error corrected, and they should be contrasted, for example, with quantum simulators that use one physical system to model another physical system. An example of this would be cold atoms, for instance. And then the interesting thing about universal quantum computers are that small sets of gates are enough to build them. So for instance, if you had single qubit rotations about 2 linearly independent axes on any 2 qubit gate, that's enough to carry out these 3 logical operations. They're enough to build your universal quantum computing system. Another set of universal operations would be this one. And then also if you just had a Hadamard gate and a Toffoli gate, which is a control NOT gate, that's all another example of a universal gate set. Right? So this is the end of like a quick overview of quantum computers. Is that any questions before I move on?
Well, I've got one.
Go ahead.
Am I the only one here, ladies and gentlemen? An example, that third bullet point, example are cold atoms. Mm-hmm. Can you give me 2 sentences on what you mean by a cold atom?
So Cold atoms is, I'm not an expert, but basically you can trap atoms in a lattice formed by lasers, right? And then you can, so basically you have a lattice of atoms, right? And they're kind of floating in space and they're trapped by lasers, right? And then you can engineer interactions between these. So, in that lattice, for instance, you can engineer the interaction between nearest neighbors or next nearest neighbors, and you can build 1D lattices, 2D lattices, 3D lattices. You can control the on-site energies, things like that. So basically, you've built a simulator, right? So if you want to study, say, I don't know, the Heisenberg model or the Ising model, in some external field, you can artificially engineer those interactions in this lattice of cold atoms, basically. And then, so it's a simulator. It's not you cannot you cannot engineer arbitrary interactions. They're usually specific, there's usually specific systems that can be studied by each simulator.
I've got a little research to do. There was a webinar today by Cold Quanta that I kind of remember. I was kind of watching it off in the corner. I kind of remember them talking about stuff like that. I'm not a physicist, so apologies. But okay.
Yeah, and so, for instance, one thing with these quantum simulators are that they are at scales that are much larger than universal quantum computers. So for instance, Chris Monroe, like in his lab, for his quantum simulator systems, they can go up to 53, 53 particles, for instance. Whereas the universal quantum computers, even though they are much more powerful in what they can simulate, they're much smaller, right? They're the limit of like maybe 20 to 30 qubits. But yeah, so basically the more control you want over the system, the harder it is to scale it up.
Oh, makes sense. Okay, thanks. Anybody else? They're quiet today. I don't know what's going on with this crew. Okay, it's all yours.
Okay. Yeah. Then let's move on to talking about NISQ computers. So, this is a popular term recently, and it stands for near-term intermediate scale quantum computers. There's no formal definition, but in general, what people mean is that basically, first of all, it's intermediate scale, so you have limited quantum resources. So then your number of qubits you have will be less than 100 typically, and actually always. There's no quantum computer I know that's universal and over like 50 something qubits, right? And another point here is that these qubits are not error corrected, so therefore your computation time is limited, right? So these systems generally favor short depth quantum algorithms. So the different ways that these algorithms algorithms that are defined. Let me start again. So algorithms. So if you want to design an algorithm that has some hope of producing something useful from a NISQ computer, you want to try to incorporate some resilience to the noise in the qubits, and there are different, and people have adopted different ways, have proposed different ways of doing that. So one example is, these variational quantum algorithms, which are hybrid routines between quantum and classical computers, and they divide work. So they have a quantum subroutine in a mostly classical algorithm, and the proofs of quantum advantage in these are mostly, so there are no proofs actually, mostly, there's just heuristic evidence that they might be useful. An example of this is the variational quantum eigensolver. Then another, another way that people think about NISQ algorithms is try to define short depth circuits. So an example is the QAOA algorithm that tries to minimize, for example, a max cut problem on some graph. Then people also do things like, you have this noisy result from the quantum computer, but often a lot of the noise, a lot of the error can be reduced by post-processing in some way. So one powerful way is doing symmetry-based post-processing. So wherein, so you get your probability distribution out from your quantum computer, and you know that some states in that probability distribution should have probability 0, but they have finite probability. So basically, that's an error, so you can discard that state. That's in my own work, I found that to be very powerful. And then there's some clever techniques again that incorporate partial measurement to decrease the degradation of performance. So for instance, we cannot correct, so in NISQ computers, we're not error correcting every single qubit or every single gate. But for instance, you can do things like, say you have an oracle in, let's say, Grover search or something like that. And you know that some qubits in that oracle are going to be in the same, so if you start them out in the state 0, at the end of the application of the oracle, they're again going to be in state 0. So if you just measure those qubits after the application of the oracle, not measure all the qubits, but just those qubits, if those qubits turn out to be in a wrong state, you can stop the computation and start again, right? So that's an idea about incorporating partial measurement to decrease noise issues. And then also an example that I'll talk about in the next few slides is you can think about how noise affects that particular algorithm, and then design a custom error mitigation technique for that. And I'll give a cool example of that in the following slides. Right, any questions over here about any of these different techniques? So in general, what I think is that, for a long time before there were real quantum computers, when this was just a theoretical field, it was very pessimistic. Like people thought that you had to error correct every qubit and every single quantum gate that was applied in order to get something useful. But what we find is that when we actually start trying out quantum algorithms on these quantum computers, even if they're noisy, you always find that the result is usually better than what you expected it to be. And it's because you can come up with all these clever error mitigation techniques, right? In some sense, what you're doing is you're making your algorithm, you're incorporating noise resilience into your algorithm itself. So yeah, just the fact that we have real hardware to play around with, I think, is going to accelerate the kinds of algorithms that we can hope to run.
So can I mean, Sonika, do you, in your daily work, is that something you personally are hands-on with?
Yes, very much so.
So could you find a simple example of some circuit you've got, hopefully simple, that you adjust because it's noisy? Could you give us a sense of what the adjustment might be? Are you doing a Z rotation, or what would that look like in a general sense?
Right. I'll talk about it in the coming slides.
Okay.
I have a couple of different examples of exactly that.
Cool.
Of a couple of these techniques. But
hey,
also,
Sonika, I've got a couple questions. So can you explain what the difference is between the variational quantum eigensolver and the quantum approximate optimization algorithm? I've seen them kind of used for solving similar problems. Which one is sort of, are they very closely related, or which one would be better for solving certain types of problems?
So basically, nowadays for these variational algorithms, there are dozens of names, right? basically have the same general idea. And the only difference here is, VQE was proposed for quantum chemistry, and then QAOA was proposed for classical optimization. But you're right that they're extremely similar. There's not any, let's say, as far as I know, any major theoretical difference. Right. I think QAOA focuses a lot on the circuit depth in the way the analysis is done, right? So people try to prove that QAOA has a speed up over classical algorithms. So they'll talk about QAOA of depth 1, QAOA of depth 2, right? And so this focuses a lot on coming up with an ansatz that can solve a problem with approximately with a short circuit depth. And usually the problems they think about are classical optimization problems like max cut. And then on the other hand, for VQE, people were focusing more on preparing ground states of quantum Hamiltonians rather than classical Hamiltonians. But they are very similar. I don't think there's as much talk about reducing the circuit depth in VQE. The idea with VQE people were thinking was more that if there was any systematic errors in your quantum hardware, it could automatically correct for them.
Thanks.
Right, and then one interesting thing to think about is there's this very cool article. It's called Supercomputing's Monster in the Closet. And it's about, whether we can actually ever expect to get to exascale classical computing. And in this article, they talk about that, classical computers at that scale are also very susceptible to errors. So there are things like, cosmic rays or transistors failing or some bit of solder that's radioactive, or, as the transistors decrease in size, they become more prone to failing, or if there's any voltage fluctuations. So all of these problems are there in exascale, are going to be there in exascale computers that are classical. And so one way that people used to deal with these problems in classical supercomputers was that they would have checkpoints in their code, right? So, at these checkpoints, whatever had been computed so far would be written to disk, so that if the computer failed at some point in the computation, you didn't have to start all over again. You could start from that checkpoint. But at this scale, what happens is that they find that the probability that an error will occur is the time to an error is shorter than the time taken to write down all the data. So it's probable that an error will happen while you're writing down your data. So you cannot really use checkpoints anymore either. And so in this article, the solution that's proposed is to make your algorithms resilient to error. And that's kind of like what we, when we talk about NISQ algorithms, like on the last page, yeah, they're also, I was saying that, we should make algorithms resilient to error instead of just hoping that the hardware will improve. So in a funny way, it's kind of a similar philosophy with, designing algorithms for exascale classical computers or for small scale quantum computers. So does anyone have any experience with this, or any remarks or comments or questions?
I have a question.
Mm-hmm.
So this article, I read the paragraphs on the left side. It mentions that there were 360 terabytes of main memory all protected by ECC. But is it saying that even the ECC memory was still having failure rates?
Yes.
Oh, that's odd, because I thought most of our, like in our standard laptops or in most desktops, we don't use ECC RAM because it's expensive, and because like for like a typical laptop, the chance of error like bit flips is pretty low. But like sure, at a supercomputer scale, you've got a lot of memory. But that's what's odd to me. I didn't see ECC as being possible for there to be an error. I thought that's like because it has extra circuitry to correct those errors.
Right. I mean, they say, for instance, right, like at the bottom of this paragraph that they were logging ECC errors at a rate of 350 per minute. So I think it's just a problem of scale, right? You know, even if your error rates are very low, but you have, you know, you're at that scale.
Big volume.
Yeah.
Yeah. Okay. Wow. That's interesting.
I personally, as a developer, I'm in denial on that. I'm going to pretend that's not going to be a problem. It just makes your software so much more difficult, or circuits in this space.
So
I mean, does it make it much more difficult, or am I just assuming that?
Well, I think you have to have a different philosophy to algorithm design, like we do with quantum computers now, right? You just have to have some error resilience built into your algorithm. So even if like you're calculating some floating point number and there's like some error in that, you know, you should just, I don't know how you would do it because I'm an expert on it on the quantum side, but I'm not sure how you would do it on the classical side, but there must be techniques. Or we have to develop techniques for that. Right, and I think it's good news for quantum computing because maybe quantum computing will become competitive earlier if there are these problems in the classical world as well, right? So, you know, I want to talk about a case study for these NISQ, a case study for NISQ computer architecture. And the problem I'm going to talk about is mapping a given quantum circuit to different connectivity graphs, right? So at IonQ, we have a trapped ion quantum computer, and in this quantum computer, you can do 2 qubit gates between any pair of qubits, at least up to quite a few qubits. You have all-to-all connectivity. So the connectivity graph would be represented by something like this, right? On many solid-state quantum computers, you do not have an all-to-all connectivity graph. You will typically have a 2-dimensional connectivity graph. So a simple, you know, one of Google's earliest devices was just, you know, a linearly connected chain of qubits. A step up from this linear chain is a ladder of qubits. So this one is, in this one, you know, basically, when I was at Intel, they liked this design very much because they could have their qubit controls coming in from the side, right? They didn't have to worry about any controls coming in from the top. So basically, if you have a 2D lattice, square lattice like this, you have to be clever about the ways in which you bring control wires to the interior of your lattice. So, you know, so these are a few different qubit layouts that are present in NISQ computers. So let's think about, let's do a case study about how we would map different quantum circuits to these different qubit layouts. So let's start with thinking about the quantum Fourier transform. So in the QFT, you have, if you look at it carefully, you have connections between every possible pair of qubits, right? So here you have a connection, you have an entangling gate between 1 and 2, 1 and 3, and 1 to n minus 1, 1 to n, then 2 to 3, 2 to n, and so on, right? So a priori, you would think that you know, you in order to perform this efficiently, you really need an all-to-all connectivity of qubits, right? And anything else would fail miserably. But then we sat down. This is part of my last job, which was at Intel. We sat down and thought about how we would perform this algorithm on a linearly connected chain of qubits. And basically, it turns out that you can do some smart things. You can insert what are called swap gates that swap the state of a qubit. And if you do this in an optimal manner, you can actually execute this algorithm extremely efficiently. So, for instance, what was happening? So, if you look here, you have a 2-qubit gate between 1 and 2, then 1 and 3, and so on, right? And then 2 and 3 and so on. So here what you're doing is you're doing the 2-qubit gate between 1 and 2, then you're swapping 1 and 2. Then you bring 1 next to 3, and then you can do the 2-qubit gate between 1 and 3. Then you swap. 1 is next to 4. You can do the 2-qubit gate between 1 and 4. And in the meantime, 2 has come next to 3. And so you can do the 2-qubit gate between 2 and 3 and so on. So you can, so the interesting thing about it is that this schedule, if you had some automated scheduling software, it would be very difficult for it to come up with an optimal schedule like this, especially, as this, if you had a very large circuit, it would probably not come up with this schedule. But basically, this algorithm has structure that, a human being, I think, can cleverly can cleverly exploit that structure to come up with an efficient scheduling of that program. And then, moving on to executing this quantum Fourier transform on a ladder, basically what we decided to do here was execute 2 copies of the QFT on the line, on these lines in parallel, and we interspersed it with these control RZ gates between the rungs of the ladder. And again, we got a schedule that was very close to the one with all-to-all connectivity, even with this limited connectivity device. Right? Any questions here?
Yeah, I'm fascinated by this. Thanks for sharing this. I haven't seen something like this. I mean, I knew about swaps, but I always thought of them as wasted operations. So it's cool to see that you're actually bringing qubits to the operations too. So you can, if you're optimal, you can use those swaps as part of the computation.
Mm-hmm.
Yeah. I had a general question. What is this process? Is there a name for this type of process?
Which process?
Just where you're transforming, based on connectivity, you're actually modifying, like rather than just calling it circuit optimization, because I view circuit optimization as like, can you reduce certain gates? Can you swap ones for others? Can you, to reduce?
So I would call it mapping and scheduling.
Okay.
Right. Mapping. So mapping the log. So over here you have these logical qubit numbers. Mm-hmm. So you're mapping them to physical qubit numbers, and then you schedule the operation. So you decide what happens at each time step.
Okay. Thank you.
Very cool. It takes me back to the days of, working in the world of assembly language before even, Fortran compilers could be trusted. You really had to work hard to, utilize that 1K of RAM in a productive way. So this is doable if you're young. Yeah. I couldn't do it anymore, man. But yeah, it's just, you need to really, you just need to really think about what you're doing. And, those of you who have used punch cards, right, you had one compile, one run a night. So you really had to think it through, but it's doable. And so this just suggests to me, okay, you got to get out of the laziness we have with classical computing now, where you just bang something out, you run and, you push run and see if it works. If not, you just fix it. This takes me back to the day where you really had to think it through, which is actually a lot more fun. And be smart about it. It's a lot more fun, frankly.
Right. Yeah, and hopefully, I think the idea is that if we solve some of these, if you can do this for some common quantum routines, right? Like the QFT is a very common, it occurs in a lot of different quantum algorithms. So then you can have, if you can hand optimize for like some of these routines, then you can, that advantage can go to a lot of different applications. Right. So that was.
But it does bring to the fore, this does get to be a learned craft. But I guess that's what you're talking about. You want to take that learned craft and pop it into some functions, or abstract it out
as much as possible. But I think there are two aspects, right? Like one is quantum computing for end users, and then there's quantum computing for people who are doing research on quantum computing, right? And I think for the end users, I don't think they should have to worry about this kind of thing. But very much so for the developers, they should be thinking along these lines, right? Like I often see that a lot of quantum software nowadays, even despite like so many years of research, they still miss so many opportunities for optimization that if a human being looked at it, they could immediately, say that, this could be done better. Yeah. So I think in both senses, I think we need to increase the level of abstraction, but also we really need to be thinking about how to make the best use of the hardware that we have right now. Right. Okay. So that was the quantum Fourier transform. So next, let's think about a common operator, which is it's called the Grover diffusion operator. So it's basically, it's a quantum version of the classical AND gate, right? It occurs in the Grover search algorithm. So basically what you want to do with this one is you want to store you want to AND a bunch of, you want to do like an AND, so whatever the state of qubit X is and qubit X, whatever the state of qubit 1 is, and that with the state of qubit 2, 3, 4, and so on, right? 1, 2, 3, 4, and so on. So how do we do this if you have a linear chain of qubits? So the idea over here is that if you have this chain of qubits, you intersperse these data qubits with ancilla qubits, right? So if you have access to Toffoli gates, you store the result of doing an AND operation between qubit 1 and 3 on qubit 2, then you do an AND operation between qubit 5 and 7, and you store it in 6, 9 and 11, you store it on 10, and so forth. And then you do an AND operation between qubit 2 and 6 and store it in this qubit 4, and so on and so forth. So you can see it over here. So you're doing an AND operation between qubit 1 and 3 and storing it in 2, right? And then you're using these swap gates to bring these ancilla qubits together, and then doing another AND operation between those ancillas and storing it on a third ancilla, and so on and so forth. You're basically in the end, you have the result of ANDing all of the data qubits in the center. Then you do a Z operation, and then you uncompute in order to make it unitary. So that was our idea for how to do this Grover diffusion operator on a line. And then when we moved to the ladder, we thought about how to do it, and we could, one way we found was to store the ancillas on one leg of the ladder and the data qubits on another leg of the ladder. We would, after doing Toffoli's in this manner, you would do the line algorithm from the previous slide on the second leg of the ladder, then do a RZ gate, and then uncompute. And these are just qualitative case studies, almost, I would say. But what we were really trying to show here was that there was so much structure in these common, quantum routines that could really be exploited. If you had a particular hardware qubit layout in mind. Right? And then similarly, we had an idea for how to do this if you had a 2D array of qubits. Right. So any questions here before I move on?
Yeah, hi, can you hear me?
Yes.
Yep.
Question, I came in a little late, maybe you answered at the beginning, but it's about Grover's. I've always had this problem with that algorithm where, how do they know when they're doing is this the one that uses amplitude amplification?
Yes, that uses a similar routine.
So that's what I have the question about, that phrase, amplitude amplification, which is a terrible phrase because they're using the same word for two different meanings. But besides for that, what is going on there? They're looking for one element and it's higher than all the others. So when they run the algorithm, it somehow uses that to come up with the right search. I'm sorry, with the target where the key is located, the search key is located. So my question is, if it makes sense, is how did they know at the beginning which one of those states to work on? You follow what I mean?
Yes. So I think you know, in answer to your question, I think for this algorithm, I think searching is the wrong way to describe it. It's not. I think a better way to think about it is it's a function inversion, right? So if you are given a function f(x) is equal to y, right? And you want to find an x that corresponds to a particular y, right? So given an output, you want to find that input, right? That's what Grover's is actually efficient at doing. But when you phrase it as Grover's search, it is confusing because yes, in order to construct the oracle, you already have to know what the answer is, right?
Right, that's what bothers me.
Right, yeah, and so, you know, it's the wrong way to think about it. It's actually a function inversion algorithm. That's where mostly in most practical applications, that's where it's going to be useful, not in searching like a database or something like that.
Okay, thanks.
Nathan, you're on a mission. Didn't you ask that same question of Will Oliver last week?
I did.
Yeah.
I got, you know, this is an endorsement of both of you. You both gave me the same answer.
Yeah, that's what I was about to say. They were like,
I'm getting,
and it was not the answer I was expecting. It was a better answer than what I imagined.
Right.
Both of you.
Right. And you said it was helpful to you when he answered it. So there must be some conspiracy here. These people are talking about me, right?
No, I think it's just we need to dial in our understanding, which is what this is all about.
Right.
Excellent. Excellent.
Okay.
Okay, that's great that Bill Oliver had the same answer.
These are the kind of things that newbies have to learn, right? These are the kind of questions that newbies will run into. They get, okay.
Yeah.
Right.
So
I think this is on actually Grover himself, because when he published that his paper, he called this paper like a quantum algorithm for unstructured database search or something like that. I think that's where the problem started. If you had just called it a quantum algorithm for function inversion, you know, there would not have been many confused people nowadays.
Yeah. Yeah. I mean, when we're trying to learn piecemeal from the bottom up, you know, little things like that would make a difference.
Right.
You know, just by the way it's called, because I had that in my brain too, until, you know, Nathan asked it the other day, and, you know, that helped me recalibrate the way I should be thinking about it.
Yes.
Yeah.
So, okay, so now let's talk about a few different applications on NISQ computers, and here I'll give some examples of you know, making your circuits or your algorithm error resilient as well. So the particular application area I'll focus on is many body condensed matter physics, and in general, what does many body condensed matter physics concern itself with? You know, this area of physics studies phases that arise from the collective behavior of many interacting particles, and so you may have heard of some of these phenomena, such as the fractional quantum Hall effect, or high temperature superconductivity, many body localization, different kinds of magnetic phases. And the very special thing about these phases is that these are emergent phenomena. So if you just knew about the underlying elementary laws, for instance, you know, the Coulomb interaction between electrons, you would not be able to, you know, predict many of these phases. So that's why they're called emergent phenomena. And basically, for these, since these phases arise from the interactions of many particles, typical approximation, approximate techniques like mean field theory and perturbation theory do not work. The time, if you want to study them numerically, the time to simulate scales exponentially with the number of particles. And therefore, we want to design quantum algorithms to study these phases. And the requirements we have of these algorithms are, one, that of course they should scale polynomially in the size of the system, in the number of particles, rather than exponentially. And second, since we're running them on NISQ computers, we want these algorithms to be resilient to noise. So in this talk, if I have time, and I may just get through like the first example, I will discuss, I made slides for discussing 3 experiments on ion-trapped quantum computers. And these are, probing transition between a metal and an insulator. It's studying the entanglement between 2 interacting electrons, and then studying the thermal properties close to a phase transition. These experiments are on between 3 to 7 qubits. The system has all-to-all connectivity. The gate set consists of single qubit rotations and then what are called XX or Malmer-Sørensen gates. And the really special thing is that it's the same system, but all these different experiments simulate a very different aspect, a very different physical system. And that really, to me, shows how versatile universal quantum computers are. So let's move on to the first example, probing this phenomenon called many-body localization on a noisy quantum computer. Now, I'm going to talk about a little bit about physics. So if you don't understand, just feel free to stop me and I'll try to explain it in simpler terms. So what is many-body localization? So basically, the idea is that if you have an interacting quantum system, it will typically be, if it's a generic quantum system consisting of many interacting particles, it will typically be thermalized, or we can also call it a metal, right? And what happens in that system, if you have this nice clean system in which if you store information in any part of this, in one part of the system, if you wait long enough, that information will just dissipate into the rest of the system. That's what it means to be thermalized, or to be like a metal. So for instance, in a metal, if you store a charge at one end, after some time, almost immediately the charge will dissipate, right? However, now if you add disorder into the system, so if you add a lot of impurities, say, what happens is that your system will have a phase transition into becoming an insulator, or in this case, what I'm called, it's called localized. So basically, if you store any information in the system at time t equal to 0, even if you wait for a very long time, you can still recover some part of that information, right? A typical model that's written down to study this effect is this, it's a Heisenberg model with disorder. I won't go much into the details of it because I know many people are not from a physics background, but basically this is the technical model that we'll study on the quantum computer. And then these are just, some things that I was describing, that when you have a localized system or an insulator, you never reach thermodynamic equilibrium. You have things like memory retention, your entanglement grows very slowly in time, etc. And this many-body metal insulator transition, there are still many open questions because classical simulations scale exponentially with system size. However, it's also very challenging to study on noisy quantum computers because, in this localized phase, if you have any noise in the system, you're basically going to destroy destroy any sign of localization. It's going to go into a thermal phase, right? So instead, what we did in this project was we design an operator, we design an observable that can probe localization even in the presence of noise, right? And these are basically what are called spectral functions of local operators. I won't go into the details unless, does anyone want me to?
Okay. I'm loving
It's not,
this.
sorry.
I'm loving this. You can go deep.
Okay, so basically, you know, if anyone has a background in like any like electrical engineering or you know any kind of engineering, you know what a spectral function is, right? Basically, you measure some quantity as a function of time, and then you Fourier transform it, right? And that's your spectrum, right? And that's essentially what we're doing here. So we're going to calculate spectral functions of local operators. So if you have a local operator is just you know is just something that you calculate from 1 qubit or 2 qubits that are next to each other, three qubits, right? So it's a local observable basically, and so that's the observable that is going to give us a robust probe of localization. And what do we expect to observe in the spectral function is that when you have a localized function, when you're in the localized phase, you expect to, when you are near zero frequency, you expect to have a suppression of the spectrum. And whereas when you're in the thermalized phase, when you're near zero frequency, you'll have a finite response in the spectrum. That's the main thing we expect to observe. So how do we calculate these spectral functions on a quantum computer? So you know, if you and you do it in just the way I said. So say you start off your quantum computer in some state at time t is equal to 0. You know, it's some arbitrary state. Then you time evolve it under your Hamiltonian, and at some finite time t, your expectation value of the observable that you chose can be expressed in this manner. And then if you Fourier transform that classically, not on the quantum computer, but classically, you will get an analog of the spectral function. And I'll skip over this part, that's too much detail, but basically all you have to do is, you know, start your system in some random state, time evolve it, and for time evolve it under this Hamiltonian describing the model, and then measure the observable at different times t, and then Fourier transform that classically. And so, you know, how do you time? So, okay, if you look at this model, right, how do you time evolve under this? So this interaction, you cannot directly implement it on your universal quantum computer. As I said, all we have are like these 1 and 2 qubit gates, and then this very special you know, interaction called the XX interaction between 2 qubits. So we obviously have to compile this down to the gates that are available on a quantum computer. And so we did exactly that. So over here, you know, you start off all your qubits in a state 0, right? You initialize them. And then you break up, you know, so you want to evolve. So you want to evolve under that Hamiltonian to time t, right? So instead of going to time t in one big step, you divide that into like m small steps. So you know, in each step you evolve by you know, by a time t divided by m, right? And so within each Trotter step, you have these 2 qubit interactions, right, that are describing the coupling, and then you have these 1 qubit terms that are describing the disorder, right? And so when these 1 qubit terms become very large, you should expect to observe the insulator phase. And when these 2 qubit terms are large compared to the 1 qubit terms, you expect to observe the thermal phase, right? And then these 2 qubit terms are further broken down into what I was calling the XX gates and single qubit rotations. So this is basically just how we compile this algorithm down to the qubits, right? And then just some details of what we did. We did 6, so for each time we did 6 steps, and you know, each step, 6 step, and then each circuit consisted of 32 qubit gates and 161 qubit gates per circuit. And you know, we're studying a disordered system here. So basically what you have to do when you study disordered system is you have to average over different realizations of the disorder. So We did that for 24 instances. And we studied it at 3 different points. So 1 point which we expect to be in the thermalized phase, 1 point which we expect to be in the localized phase, and 1 near the phase transition. And so what do we observe, right? So here are the results. So sorry, I forgot to put the x-axis label. But on the x-axis is the frequency, right? And on the y-axis is the spectra. And this line is the theoretical result, right? At the 3 different phases that we are probing. And then the points are the experimental result for the spectra. And you can see that, okay, it follows the general trend, but it's quite, there's quite a large error. And like if you didn't have the theoretical line, if you just had the results from the quantum computer, if you were just comparing the points between the blue and the red and the yellow, you might think that it's just the same phase, right? There's nothing much that's different. What you want to observe is that at low frequencies, not zero frequency, but at low frequencies, if you were looking at just at the theoretical data, you would see the suppression in the response, right? And so what we did is, we looked at how the noise is going to affect the output of the algorithm. And we found out, we went through the steps and we found out that we could actually eliminate the error by just, A is the spectrum. And if you divide the spectrum by its value at 0 frequency, you can basically get rid of all of the error. Right. So in this case, we divided both the theoretical and the experimental spectrum by their respective values at 0 frequency. And now you can see that the experimental results lies all within error bars on top of the theoretical result. So, I just want to emphasize how amazing this is. Like if you look at how many gates we did 32 qubit gates and 116 1-qubit gates per circuit, right? That means like if you run the numbers on what the gate fidelities were, you would expect to have not more than 54% accuracy for the output of this algorithm. Yet we designed an error mitigation technique. It required no extra measurements, but you basically have, perfect answer, perfect fidelity here, just by going through and thinking how the noise affects the algorithm, right? And so now if you were looking at, if you were thinking about this system, you would very clearly see, like when we look at the spectrum at low frequencies, you clearly see that it's suppressed, right? As you go from high value of J to low value of J. So any questions here?
I've got one, and this is at the risk of showing my ignorance, et cetera, but I'm from a position of I know I don't know what I'm talking about, but it kind of reminds me of learning about machine learning a decade or two ago, of the notion of overfitting.
Mm-hmm.
Am I mixing apples and oranges here, or is that where you've got a theoretic objective and you've got in practice, and in this case you can get them to match pretty well, but
Mm-hmm.
it's a solution that is for a very specific problem.
Yes,
and
of course.
it's not generalizable.
Well, so I agree. So this solution is particular to the study of disordered systems, right? And there were a couple of tricks that we played, right? One was that we made, no matter what time we evolved to, we made the number of trotter steps the same for all times, right? So, but this is what I mean about the design of, you have to design your algorithm to be resilient to noise, right? And that design will be specific to each algorithm or specific to each class of algorithms. So now, when people talk about quantum error correction, that's very universal, right? Right? No matter what your algorithm, you know how to correct your C0 gate, you know how to correct, your Toffoli gate, etc. But that's very expensive, very hard to do. On the other hand, like when we're designing each quantum algorithm, right, we think about how the noise in the quantum computer is going to affect the output of this algorithm. And then you try to think about how can you reduce the effect of the noise. And that the technique you may come up with may be very particular to that particular algorithm or to that particular class of algorithms. But, you know, if it gets you results, that's cool. You know, I will say this, that we didn't need to know the answer before we designed the error mitigation technique. We could design the error mitigation technique before we knew the answer.
I think I follow you. I think I follow you. Yeah. Yeah.
Yeah.
Any other questions?
All of this derivation didn't need to know what the answer was. All we did was divide by the zero frequency.
Mm-hmm. Amir, yeah, go ahead.
I've got a question. Okay, so I'm seeing that we're essentially renormalizing to that first value, the first frequency.
Exactly.
What I'm missing is how, well, okay, sorry, one just mechanical question. How come the error bars adjust? I'm not used to these plots, so I'm just curious, how come the error bars adjust when you renormalize? Is that just an effect of dividing through?
Yes.
Is that
So
when you
combine the error bars, at least this is from the theory of errors, right? When you combine errors, you increase the error.
Okay.
So because you have an error in the zero frequency and in the finite frequency, right?
Yeah.
Then you're combining them. And also this is a much more zoomed in scale. So that's why also they're looking bigger.
Yeah, and that's because we're renormalizing to that first value.
Yes.
But what I'm misunderstanding is how did you reach the conclusion? I guess you're also overlaying the line as the theoretical or the calculated value. And when you divide that, you're saying when you also divide that number by the first value that the two coincide.
Say that again.
Yeah, I'm not being too clear.
So basically, the experimental data is divided by the experimental zero value, and the theoretical data is divided by the theoretical zero value. We're not mixing data. Okay. We're not dividing. We don't need to know anything about the theory to process the results about the experiment.
I see. And you're just showing that when you divide them both by their first frequency, that you get the almost the same values.
Exactly. Yeah, exactly. And so it is model independent. No matter what disorder model you use, right? If you were studying a disordered system, you could do that. And it's not that there's no cheating involved, that I needed to know the answer in order to do this post processing. If I didn't have any information about the lines, I could still post process the points.
So not knowing how this solution is used, is the relative value of value over having the absolute, because you're going to lose that absolute information.
Yes. And yes, and that's a good point. And it turns out that if you go back to the the theoretical model, like I didn't go into that over here, but into how the spectrum is supposed to look, it still works, right? It's not that it still works. Even if you have the relative value, you still can see the suppression of the response at low frequencies, and which is what we were probing. That as you go into the disordered phase, the zero frequency response goes down.
Great, thank you.
Yeah.
Hi, David Garvin here. Thanks for a very interesting talk so far, Sonika. Just following up on what you were just saying there and what Amir was asking. So when you're dividing by the zero frequency amplitude, so that's effectively dividing by a constant, if I'm understanding correctly.
Yes, it's a constant, but it's different at different values of J.
And which is then, so it's a different value as you're moving across the x-axis on the plot. Is that right?
Well, for the different panels, it's different values, but it's constant at, so for instance, at J is equal to 0.7, it's this value for the experimental data. At J is equal to 0.3, it's this value.
Yeah. Okay, yep. So like if you refer that back to, you don't need to move it, but like the few slides earlier where you were actually showing the spectrum distribution, then, so if you did dividing by a constant, I mean, it's not going to change the shape of that distribution at all, correct? So,
yes, exactly.
I'm not clear how that then reduces the noise impact just because you're dividing by a constant.
Right, and so for that we built an error model, right? So if you go in and analyze what's happening, it turns out that for when you're simulating disordered systems, right? No matter what the source of your error is, if you're simulating disordered systems and which is essentially equates to simulating random circuits. So no matter what the source of your experimental error is, if you are calculating, some average quantity, the way it's going to manifest is through what's called a depolarizing error model. So basically what happens is that, say the error in your circuit is epsilon m, right? Then you can write your quantum state, your average quantum state, as epsilon m, right? So epsilon m is not the error, but epsilon m is the probability of getting the correct answer, right? So you can write your average quantum state as the probability of getting the correct answer times whatever quantum operation you did, plus 1 minus the probability of getting the correct answer times an identity matrix, right? So this is just like a fully thermal matrix, right? There's no information in here. And then the probability of having the correct answer is epsilon m, right? And so what happens is, when we calculate, the expectation value of this observable, and we say that this epsilon m is, some probability of getting the correct answer in one Trotter step to the power of the number of Trotter steps. So, if you go through and calculate it, what you see is that when you're calculating this value A, right, the average value of A, which is the spectral function, so you get this p to the power of m as p to the power of m, where p is the probability of getting the correct answer in one Trotter step, times the correct answer, right? So basically, since p is less than 1, your value of A is always going to be suppressed compared to the correct value, which is also what we see in experiment, right? And then but what happens is that if you set omega equal to 0, this factor remains the same. You're again going to get p to the power m. So if you divide this omega by omega equal to 0, you cancel the p to the power of m, right? Does that make sense?
Yes, that helps a lot. Thank you.
Right.
Can
I don't know if
is it possible for you to give or put some references into the chat thing or
sure.
something like that?
I have a reference. I have a slide. I'll share it at the end. Maybe you can take a snap. Yeah.
Good. Thank you. Thanks for that. Sorry to take up all the time.
No, that's fine. I hope that was kind of complicated to explain in words, but
it's very interesting though. I've been looking at various error mitigation techniques, but I hadn't seen this way before.
Yes. Right. And it's interesting. You could have divided it by any frequency, but then you wouldn't have, you want to do it by the frequency that doesn't matter. So the 0 frequency doesn't matter over here.
Yep.
Okay, and so maybe I'll skip this part in favor of just quickly, how much time do I have left?
Sonika, with your level of expertise, you could go all night if you want.
Okay, maybe I'll go over
I mean,
one.
you're in
more.
Portland, so I think you've got a very interested audience here. Would that be fair to say, guys and gals?
Yep.
You can go all night if you want. I'm learning a lot, and I think many of us are. So
Okay, cool. So,
it's up to you, entirely up to you.
Okay, so I'll at least go over one more of these experiments.
Okay. And let me add, I believe your book did, this is kind of like a rock concert. So you have another show booked with the Portland meetup group, I think in 2 or 3 weeks. So let's keep that in mind, everybody. We can come back for more later.
Right, and I'm talking about something different at that time. So.
Oh, okay, great. It's like the Grateful Dead. Every show's different. Excellent.
Okay, cool. Thanks for the compliment, I guess.
Yeah,
Okay.
yeah. That's a good thing, I think.
You know, in this experiment, basically, as a overview, what we had done was we calculated these. We designed an observable, which was a noise resilient diagnostic of this phenomena that we want to study. We showed that they can be computed efficiently on a quantum computer. We measured them on 3 qubits, and then we designed an error mitigation technique that basically we can extend it to without significant fidelity loss to larger system sizes, we think. I think there are still some caveats in terms of like you have to increase the number of shots that you need to get, but that's that's usually true of any error mitigation technique. Okay, so let's move on to measuring what's called the Renyi entropy of a two-side Fermi Hubbard model. Okay, so this is a completely different topic. So what are Renyi entropies? So say you have a many-body quantum system, and it can, this quantum system is defined on 2 subsystems A and B. So you can write the state of the system in this form, right? So the degrees of freedom in A are written as AI, and then the degrees of freedom in B are written as BJ, right? And then the state psi of the full system is some superposition of states AI BJ, AI tensor product BJ, right? Then what you can do is, if you're just interested in the system A, you can write down the reduced density matrix of A, and by doing what's called a partial trace operation, that you basically you forget about the degrees of freedom in B, and you're just concerned about the degrees of freedom in A. And so this rho A is a square matrix, and you can define its eigenvalues. It has real eigenvalues. And then you can define what are called the Renyi entropies. So basically, the Renyi entropy is related to the log of Rn, where Rn is a sum over powers of the eigenvalues of this reduced density matrix of A. And basically what these Renyi entropies do, they define the entanglement structure of the problem. So for instance, if A and B were entangled, right? So if psi was not a product state between A and B, but there was actually some entanglement between subsystems A and B, then R2, so if you had n is equal to 2, the second Renyi entropy would be less than 1.
A quick question,
right?
please.
Go ahead.
Isn't there also a von Neumann entropy there? How's that different? Is that because the Renyi's on the trace and the von Neumann is, but the von Neumann entropy also measures the amount of entanglement, right? Here.
Yes, and I'm forgetting, but I think the von Neumann entropy is the limit. I think when S is equal to 0, not S, sorry, when N is equal to 0, right? Then you can get the von Neumann entropy. It's something like that, right? So when you have positive integer values of and you get the Renier entropies, and then the von Neumann entropy is a limit of that, of n tending to some, I forget whether it's 0 or -1 or something like that.
Okay.
Right? Yeah, but von Neumann entropy also probes the entanglement. You're right. And but the problem, okay, yes. And so why am I talking about Renier entropies? And von Neumann entropy is a common, it's a commonly known known thing. But because von Neumann entropy is like I don't think there's any known technique to measure it efficiently. Like you can measure if you want, if you wanted to measure it, you could characterize the entire density matrix, but that would take time exponentially in the size of the system, right, in the number of qubits. But however, I'll show you techniques where you can measure these Renier entropies that also characterize the entanglement, but you can measure them efficiently on the system, right? And so even with just R2, which is the second Renier entropy, there are many applications. And here I've written some applications in condensed matter physics where you can probe different kinds of order, you can study phase transitions, etc. So how do we calculate R2 on a quantum computer, right? It turns out that, so, here I define the state psi, right? Now, if we prepared 2 copies of the state psi and we measured the swap, we measured the expectation value of an operator that swaps the degrees of freedom in just subsystem A, right? That will give you the Renier entropy of subsystem A. Right, and so how do we define this operator swap of A? So if you have, these 2 copies of psi, so you can expand each psi in this way, and then when you are applying the swap operator here, you see that Cij and Ci dash, the coefficient will go to instead of being a coefficient to Ai Bj, Ai dash Bj dash, you're basically swapping Ai dash with Ai, right? So, we also know that to measure the expectation value of any operator, what you can do is if you have some quantum state, you can put an ancilla qubit in a superposition and then operate a control version of that you can apply a control version of that operator and measure the ancilla qubit. And that measurement will give you the expectation value of that operator. And so that's exactly, so, we put these 2 ideas together. So knowing that, we want to measure the expectation value of swap A, and to do that, you need an ancilla qubit. We put those 2 ideas together to design a circuit like this. So here psi is the state psi, right? So it consists of these, the degrees of freedom in A and B, right? And then A and B. And then you apply a control version of the swap operator, right? And it's controlled on an ancilla that's in a superposition. And then you measure this ancilla. You get the expectation value of the swap, which in turn gives you the Renier entropy, right? Sorry, any questions here? No? Okay. Can people still hear me?
Yes.
Yes, okay, cool. Sorry, I thought that maybe I went offline. But okay, so we want to measure this. So we have a circuit to measure entanglement between 2 subsystems, right? Okay, so how do we? So let's try it on some some model. So for this, we pick the Fermi-Hubbard model. So I don't know if people are familiar with it or not, but Fermi-Hubbard model, it's a popular candidate for explaining high temperature superconductivity, right? And it basically consists of, I don't know if people know how to read these operators, but basically what it is it consists of electrons hopping on a lattice. So, this operator, this term consists of the kinetic energy of the electron. So you're basically destroying an electron at site J and recreating it at site I. So that's the kinetic term. And then this is the interaction term. So, if there are two fermions on the same site, that gives them an energy penalty of U, right? And so let's start with the simplest version of this model, which is just, it consists of two sides. And so on each side there are two electronic orbitals, right? And they correspond to spin up, spin down on one side, and then spin up, spin down on the next side. And then the energy penalty U, and then the probability of tunneling T. And so these are electrons, not qubits. So if you want to model them on a quantum computer, you need to do what's called a Jordan-Wigner transform, right? And if you do this very naively, you find out that each electronic orbital you map to one electronic orbital maps to one qubit. So you map 4 electronic orbitals to 4 qubits, right? And you get this Hamiltonian, right? Okay. So that's one way to do it, but let's try to be smarter about it. And you find out that this 4-qubit Hamiltonian, if you actually write it down, it's extremely sparse, right? So maybe we can do something smarter. And in this case, what we are going to do is that we know that in this Fermi-Hubbard model, this Hamiltonian conserves the number of electrons. So basically, if you start out with 2 electrons in the system and you time evolve with it, in the end also you're going to have 2 electrons. So basically, no electrons are destroyed or created. So that gives you one symmetry property with which you can reduce the size of the matrix you need to simulate, and you end up with a 4x4 matrix instead of the 16x16 matrix. So that's an example of choosing a clever mapping, right? So instead of using that naive Jordan-Wigner mapping, we're going to use a smarter first quantization mapping, in which instead of trying to map the 16x16 qubit matrix, we're going to map this 4x4 matrix to qubits. And if you try to, so this matrix, you can actually write it down very simply in terms of Pauli operators like this, right? And in this, your physical interpretation of what the qubits are doing is that one qubit represents, the fermions being in an upspin space, and the second represents the downspin space. And so what are we going to do now? We want to measure the Renyi entropy at some point in the phase diagram, which is characterized by U, so we want to extract the Renyi entropy at some point in the phase diagram. And how do we prepare our qubits at that point in the phase diagram? We do that again by using trotterized time evolution. So, in the beginning, your qubits are all in the state 0. Right, and so if you evolve them very slowly from from a 0 interaction state to a finite interaction state, by the adiabatic theorem, they should, with high probability, lead you to the correct phase at the finite U. And basically, here's like putting all the steps of the algorithm together. So remember, so here, this is complicated because we're putting a lot of different things together. So the first thing you should know is that, so each copy of the model maps to 2 qubits, right? And we have, initially I was talking about how you need 2 copies of the system to give you the second Renyi entropy. So we have 2 copies of the system, right? Initially they're all prepared in 0. The first qubit, we'll call it subsystem A. The second qubit is called subsystem B, and similarly for the second copy. Your ancilla is initially prepared in the state 0, right? Then after you prepare the qubits, you implement this trotterized time evolution to adiabatically evolve them to some finite value of u, then you do this measurement of the second Renyi entropy by implementing this controlled swap gate, which is controlled on this ancilla qubit that is in a superposition. Right? So a lot of different elements go into compiling this algorithm down to qubits. But finally you have this quantum circuit. You can do different, so there are different kinds of errors that happen. So, we don't have infinite computation time, so there are different kinds of errors that occur when you do this mapping. One error comes because, you cannot do this adiabatic evolution to infinite time. You can only do it to finite time. So you can, so there's a parameter tau that defines how long you're doing the adiabatic evolution for, and you can check your errors as a function of tau. And then there's also an error that comes from the trotter step size, delta, and you can check your errors as a function of that. But, and then if you look at this diagram, we have everything has 1 and 2 qubit gates, which we know how to implement, except for this operator, this controlled swap gate. Right? That's a 3 qubit gate, and that's not directly implementable on the trapped ion system. So this was compiled down to a number of 1 and 2 qubit gates, right? So it's an example of compiling a high level quantum operation down to lower level quantum operations. I'll skip this one. Let's look at what happens when we measure R2 as a function of U, right? Let's look at the diagram on the right. So when you, sorry, what happened? Sorry, I'm missing some, sorry, I'm missing a curve. Sorry about that, it disappeared. Basically, this is the result for measuring R2 as a function of U, right? Let me go over here. So this is the result for measuring R2 as a function of U. So on the x-axis is U, and on the y-axis is the Renyi entropy. And the blue result, again, is the result from theory, and the original result from the experiment were these purple points, right? And then you can again see that this is, it looks like such a large error, right? This is the blue curve. If you compare the blue curve to the purple curve, there's almost like, if this is 50% and this is around 70%, you can see how large of an error that is, right? It's almost unusable. So then again, we went in and designed another error mitigation technique, right? And this time what we did was that we knew that here we are calculating the expectation value of the swap operator, and we know that the swap operator has even and odd eigenstates. And so what we know is that if we measure the ancilla qubit in a state 1, it means that the data qubits can not, the data qubits, the corresponding data qubits in the in the two systems, in the two copies that we have prepared, they cannot be the same. Long story short, what we can do is we can design sort of a filtration technique, right? So you get this noisy, so in the top we show the noisy output from the quantum computer, right? And we can design a filtration technique that throws away some of the states, and you get this, you get this, and after you apply that filter, you get the probability distribution on the bottom. And you can see that going from the uncorrected data, once you apply that filter, you get your corrected data again lies almost exactly on top of the Johri curve, right? So again, this is another example of how you can design error mitigation techniques that will significantly reduce the error. So any questions? I know this was a bit confused.
Yes. What's the difference between theory and exact?
So the exact curve, it's obtained from exact diagonalization, right? The theory curve, so remember I said that there were errors that came in the design of the circuit itself, right? So the theory curve is if I simulated that circuit on a simulator, on an ideal, it would be the output from an ideal quantum. So this is the output from an ideal quantum computer. This is the output from exact diagonalization. Does that make sense? So there are errors that will come in the design of your circuit itself, and then there are errors that will come in executing the circuit on the quantum computer.
Yeah, and is this from, I'm forgetting now if the Jordan, when you were describing Jordan Wigner, was that in this experiment or the previous one?
This one.
Yeah, so so I think what you're saying is because we chose not to go with the Jordan Wigner encoding because you chose a different one, I forget what that was, that's where we're gonna deviate from exact, right?
No.
Oh.
So that was exact. So this one was exact, right? So instead of the Jordan-Wigner mapping, we used the first quantization mapping, and this one was exact. Where the errors came in is in these parameters tau and delta. So delta is the Trotter step size. So basically, what happens is that this Hamiltonian, you cannot implement it exactly on the quantum computer, even though the mapping is correct, right? This is an exact Hamiltonian. But in order to time evolve under this, you have to do what's called Trotterization. And there's a Trotter parameter delta. And as you increase delta, right, as you increase delta, you reduce the number of gates you need to do, but you increase the error, right? Then the other error comes in from, you're doing this, what I would call digitized adiabatic evolution. So you're taking your system from zero interaction to finite interaction, and if you do that over a long time, your error will decrease. But if you did that for a long time, you would need more gates. So basically, the theoretical errors are coming in from having a small circuit depth. Does that make sense?
Yeah, it does. It seems like, because in a traditional, if we were actually adiabatically computing this, it would be a continuous operation, correct?
Yes.
Yeah. And if
Right. Yes. And it would be a continuous, and if you did that for a very, very long time, you would have much lower error, right? But you're doing it for adiabatic theorem holds, in the limit of infinite evolution time, but we're using a finite evolution time. So that's one source of error. And then discretizing the time evolution is the second source of error.
Great, thank you.
Right. So over here also we had almost 40% reduction in error just by using this simple post-processing technique. Right, and it didn't require any extra data or any extra operations on the quantum computer. Right. Okay, so I think I will end here. This next topic I'm going to talk about in my talk in a month's time. So I'll save it for then, and I will I will leave people with my references in case anyone wants to take a screenshot of that. Are there any questions?
Yeah, I have one more. Thank you for the talk. I know nothing of physics, but I still attempt to try to understand. The question I have is, so I'm seeing that you're doing this on your 6-qubit device, and obviously that's a device that we could simulate. We could simulate using a classical computer. But what I'm starting to understand is the idea here to figure out methods that will be noise resilient and ones that you can verify, so that when we do move into the realm of 50 plus qubits, you can relax into knowing that your answers are still probably correct.
Right. So just to correct the first thing you said, currently IonQ has 11 qubit systems available publicly, and these were all experiments I did in the past at the University of Maryland, and they had up to 7 qubits. But yes, what you said is essentially correct. So we try to work with the hardware we have and try to design these error-resilient quantum algorithms, right? And exactly, we can. The idea is to run them on, for success. As the systems improve, we can run them for successive system sizes, and get a good sense of what the errors are and how to reduce them. And so that when we have systems that cannot be verified against classical computers anymore, then you can rely on the results.
Great. And I'm curious, are there problems in the 50 qubit space that you are excited about personally, or that you think would provide answers that we're unable to get right now?
I think
qubits.
there are a lot of things. I think we of course have these problems in quantum chemistry and condensed matter physics and material science, but there's also a lot of promise in optimization. I mean, there's all kinds of things actually. So there's optimization. Recently, there have been a lot of interesting machine learning methods for noisy quantum computers. So typically, when people were talking about quantum machine learning, there was always this problem of how are we going to get the data into the quantum computer. But now people are looking at techniques like doing generative machine learning, or doing, speeding up certain subroutines of machine learning on a quantum computer, which do not require the construction of a quantum RAM. So I think those are also promising for like 50 qubits. And there are other things, right? Like we were talking about Grover algorithm earlier, right? And then there was this paper that I wrote with a collaborator called Quantum Solution for Efficient Use of Symmetries in the Simulation of Many Body Systems, which was basically using the Grover algorithm to block diagonalize a matrix based on the symmetries of the matrix, right? So yeah, I mean, and we showed how to operate it on a noisy quantum computer. Like, I don't know exactly at what point it would be, at how many qubits it would need to be useful, but I certainly know that if I had a noisy quantum computer with partial measurement, I could run it, right? Yeah, I think, simulation of many body systems, optimization, machine learning, and maybe even more things. I don't want to rule anything out, because every day I learn more about how to operate these noisy machines.
Thank you. Yeah. That answers my question partially. I'm sorry to keep digging
Yeah, go
on
ahead.
this. I guess if I could ask more clearly, what I was wondering is, are there, in the physics realm, are there, like for instance, I took part in this Qiskit summer school, and we did calculating the ground state of lithium hydride, and so these are like toy problems to work with, because they're tractable even on a classical computer. I guess what I'm wondering is, are there already in physics or chemistry or candidate problems that are beyond the reach of our classical computers that we're hoping to solve soon?
Okay.
Yeah.
Yeah. So, okay. So my best guess for that would be something like, as far as the physics problem is concerned, would be something like the dynamics of spin chains near critical points, let's say. Does that make sense? So spin chains, because we don't need an expensive Jordan-Wigner transform. Spins have one-to-one mapping with qubits, right? Dynamics, because you can just do a tortoise time evolution. You don't need to do phase estimation or any complicated algorithm like that. You can just trotterize and do the time evolution. So that should take relatively fewer qubits. And dynamics of spin chains near critical points. So a critical point is a point near a phase transition between two phases of matter. And most of the classical computing techniques will fail near critical points. Because people have all these tensor network techniques and DMRG and all these techniques, but they work far away from critical points typically. So, but a quantum computer is not, it doesn't have to make the same kinds of approximations that those classical techniques make. So, I think that's a good guess for what's going to be maybe the first few problems that you will get useful information from a quantum computer that we wouldn't from a classical one.
Awesome. Thank you.
Should I stop sharing chat?
Carol, I think you're muted.
There. Is that better now?
Yes.
I got a backup system here that chooses to go off every once in a while. Anyway, thanks for the marathon round. You gave me and many others plenty to think about. And definitely, this is one of those, I got to watch it again because I know I missed a lot of stuff. It's like a really good movie, you got to watch it again. But don't forget, folks, we got a return visit in Portland in, what's it, 3 or 4 weeks? So watch Quantum-A-Palooza for that. Playing some different music, I guess. So that's cool. Also, let me just quickly mention on the side, tomorrow there are 8 quantum events. So check out Quantum-A-Palooza. There are 8 starting at 5 a.m. and ending at 9 p.m. Eastern time. And they're all very different. And for people like Jamie who just can't get enough of this stuff, none of them overlap. So you could participate in all 8 events. And they're all very interesting, quite frankly, including an interview with Scott Aronson coming on at 3:30 Eastern time. So, that's always a joy to see him talk. Anyway, for tonight, that's it for tonight. Sonika, thank you very much. This was a lot more than I was expecting. Honestly, when the title was Applications of NISQ Computing, right? I actually framed this as a level 100, but I think this is a level 300 which is much better, frankly, in the depth and all that kind of stuff. So it's always welcome, particularly with this crew here. So any last minute comments, questions?
There were a couple of questions in the chat,
sure.
but I never answered them. I just saw, and thanks everyone. There were so many good questions. Can you talk a bit more on the usefulness of the partial measurement from the NPJ QI paper? Yes. So basically, with partial measurement, so much like a conventional quantum error correction, where you use partial measurement to project out errors, it's similar. If you have here, basically, it's almost like a quantum if statement, right? What you're doing is if at some point in your computation, you know that your qubits are going to be in a classical state, you can measure your qubits at that time and those particular qubits at that time, And if they're not in the correct state, you say that there's already been an error in the computation, you stop and you restart, right? Instead of continuing with the complete circuit and then getting a very noisy answer, and then you stop, you project out the error mid computation. That's like a high level way to explain it. If you actually read the paper, there's a very nice example of how that's done. And if you have more questions, I would be happy to answer over email also. And then there was one more question. Is this, I'm not sure what that's referring to. Is this a quantization error that is then being mitigated by a transform to reduce the error's impact? That's from Lalit. I'm not sure which one.
Lalit's still on. Can you speak to it, Lalit?
Oh, there's a new, for the Rennie example?
Yeah, basically you're removing, there's a quantization error that's coming introduced as a function of the way you're sampling through it.
So I wouldn't call it a quantization error. Yeah, I mean, it's just noise, right? That's producing states in the end that are not supposed to be there. But what we're doing is that since we know from the symmetry of the problem that those states are not supposed to be there, we just throw them away and renormalize the rest of the probability distribution.
So you're just doing an error threshold transform on it and just dropping below that threshold? Is it at the end when you look at the curve before and after the transform that you do?
Say that again?
In one of the, probably should have been done when the slide was there, but you're showing a waveform where you have all the noise in it, and the next one, the noise is mitigated between there,
Yes.
and you're picking up basically the spectrum or peaks differently, and those are the points at which the Rennie comports to that basically. That's what you're doing in the sense. That's my pickup of it.
Right. Like I wouldn't describe it quite that way, but I would just describe it somehow as a noise filter, right?
Okay.
Yeah.
Noise filter. Okay, cool.
Okay, cool. Thanks so much for setting this up, and it was great to talk to this group.
Hey, anytime you want to come back and talk, you just send me an email. We'll set you up any date and time.
Okay.
This is good stuff. It's very interesting. It's not, it's actually pretty difficult to get to someone like you with the depth of knowledge and be able to ask questions like this. So this is really a treat for all of us. So
Okay.
I maybe throw out one more question.
Sure. Go ahead.
go, David.
So I see you at IonQ now, and previously you were at Intel. Can you maybe talk a bit about the differences between their computers, QCs?
Okay. So
besides the obvious of it, of ion trap versus not, but the more interesting things.
Right. So it's they're very different technologies. So Intel is pursuing solid state qubits, right? And that's in keeping with their philosophy of they're a leader in making transistors, right? So that's why that was one of the reasons they were pursuing silicon qubits, right? Silicon quantum dot qubits, because that was very compatible with their fab. And at one point they were also they recently shifted more of their focus to silicon qubits, but when I was there, they were also working on superconducting qubits, right? And this was all done in collaboration with Delft University. So with the solid state qubits, there are advantages and disadvantages compared to trapped ion qubits. The solid state qubits, they're faster, right? Like the gate times are several magnitudes lower than the gate times in the trapped ion quantum computers. But the trapped ion quantum computers are much higher fidelity. The solid state quantum computers, they typically have very limited connectivity, so they can only be like nearest neighbor connected on a line, or maybe some lattice like that, the line lattice example I showed. Whereas with the trapped ion qubits, at least up to like, several dozen qubits, you are going to have all-to-all connected systems, right? So that automatically reduces the number of, swap gates that you have to insert. there are issues of scalability, and I don't want to make any big claims about that. There are people who say that solid state systems are not that scalable because of the wiring issue. Then there are people who will say that the ion trap systems are so big compared to the solid state systems that how are you going to scale that? I think there are also differences, and we haven't seen much of that practically yet in the commercially available systems, but I think the kind of error correction techniques that will be pursued will also differ significantly between the two systems, between the technologies. Yeah, I mean, yeah, we talked about speed, we talked about scalability, we talked about error correction.
So, Sonika, this is Lalit. Do you see solid state merging, and there's work that goes on around doing the silicon photonics happening, and so you can do a lot of stuff with photons in there that allow you to look at both distance and create a more fully connected mesh differently than you would do with just a next neighbor, or close by solid state gates, if you want to call it.
So yeah, there are some, I don't know if any such system has been built, but there are talks about, like, instead of having like a monolithic chip, right, with like a lattice of qubits, you could have many chips that were connected by photons. And that's actually also true in the trapped ion systems, right? You might have a small quantum computer network, right? So instead of having this long chain of ions that's growing and growing, you have these different chains of ions that are connected by photons. I think that's true. I think that is actually a path to scalability.
Exactly. It's a chiplet system where you bound error within a certain spectrum. So you keep it in smaller size enough that allows you to manage whether you're trying to do cooling on it. The superconductivity at scale will become a challenge. I mean, you can do certain things, but beyond a certain point, it'll be for the aficionado like us on this call, but beyond a certain point, you need to solve it in a different way. So that's kind of the take. And there's some going on in some places that can be.
And that will come with its own set of mapping and scheduling problems, right? Those interesting problems of how do you take this theoretical circuit and how do you actually execute it on this network of connected quantum computers. And I don't think people have quite started working on that yet, but it's certainly coming.
There are some stealth, but yeah, soon enough. We'll see.
Okay, well, goodness. Thanks again. I don't know how to repay you. This is terrific. This is terrific.
No, this was super fun. Thank you.
Okay. Well, come by and visit as a participant, I guess a participant as well sometime.
Yes, I will.
Pretty cool talks.
These events. Okay.
Cool. Anyway, good night. Thank you.
Good night.
Thank you.
Appreciate it. See you all later.
Thanks, everyone.